Okay, students, so in this note set, we're going to take a look at the most modern and up-to-date theory of the atom that we have at present. It's called the quantum mechanical model, or sometimes also known as the wave mechanical model, or it's even gone by the name the electron cloud model. All of those names apply to the same thing, and it's the most modern understanding of the atom that you have. You might wonder, well, then why did we bother learning about the Bohr model or the J.J. Thomson plum pudding model or any of the other models that preceded that? Well, in coming to a deeper understanding of the atom, we've gotten to a point where it gets really, really complicated. Even as we cover this most recent model of the atom, we're going to skip over just about all of the math that lies behind it. We don't, it would take graduate level calculus in order to come up with some of the conclusions that we're going to draw today. So the basic gist of it is we're trying to walk students through an understanding of the atom in a specific order so that they can grasp the key stages as we go along. That's why it's introduced in this way. So first, let's give a basic overview of the quantum mechanical model. In this model, we're studying the wave-like rather than the particle-like nature of the electron. Think back to the first note set in this unit where we talked about light having both a wave-like nature and a particle-like nature. And up until now, we've been focusing on photons, the particles of light being emitted from atoms. But there's another half of the story, and that other half is the wave-like nature, not just of light, but of all things. All matter, even larger pieces of matter, have at least some wave-like nature. And honestly, we've not quite grasped, even at this point, the full consequences of the wave-like nature of matter. There is a lot of future research to be done in this area. But when coming to an understanding of the atom, the electron is a small enough particle that the wave-like nature does indeed matter, or have importance, I should say. In chemistry, everything matters. Here is the scientist who first proposed the wave mechanical model. His name is Erwin Schrödinger, and the gist of his work is that he found a way of predicting where an electron would be in an atom. We knew that electrons are somewhere outside the nucleus, and Bohr said, hey, they orbit the nucleus just like planets orbit the sun. But it turns out that whole model, the Bohr model, broke down with more complicated atoms. It did a great job of describing hydrogen and even helium, the next larger element. But when you have lots of electrons around in neutral atoms of larger size, it just didn't predict how those atoms would bond together. And so, using really high level physics, Schrodinger developed what's called the wave function. The wave function gives the probability of finding an electron at a certain distance from the nucleus. So if you take a look at this graph, it says radial probability. It means the likelihood of finding an electron plotted against distance from the nucleus. As you move to the right on this x-axis, you're getting farther and farther away from the nucleus. So if this graph showed one electron's likelihood of being found, you would say, hey, its peak probability is at this distance from the nucleus. The solutions to the complex math of Schrodinger's wave function are not just a single number, they're actually three-dimensional shapes. And those three-dimensional shapes represent the regions of space where you're likely to find electrons. Now, some of the shapes get quite goofy in appearance, and we're going to take a look at some of the goofy shapes, but we're not going to go anywhere near the more complex ones. In other words, what we're going to study in this unit isn't anywhere close to where modern physics is taking us. It's rather, consider it a stepping stone to future studies if you're so inclined. There's a name to the three-dimensional shapes that are solutions to Schrodinger's wave function. The name is a little bit misleading and unfortunate. The name for the three-dimensional shape is orbital. Now, some people get that confused with the word orbit, understandably. In the Bohr model, Bohr suggested that electrons orbit the nucleus just like planets orbit the sun. But the word orbit in the Bohr model has no relationship to the complex mathematical solution that is a three-dimensional shape in the wave mechanical model. Okay, so orbital is a three-dimensional shape, and orbit would be like the circles in the Bohr model. Okay, now this is gets a bit philosophical, but it's important for understanding why we need to go this direction. It's called the Heisenberg uncertainty principle, put forth by Werner Heisenberg. Oh, wrong picture. There he is, Werner Heisenberg. Heisenberg discovered that you can't know both the momentum and position of a small particle like an electron at the same time, because the electron is constantly interacting with the fields of energy around it, which includes any field of energy that would allow it to reveal its position. The consequences of that may seem, relatively straightforward. All right, there's a small particle. I can know its momentum or I can know its position, but I can't know both. Doesn't make a big difference in terms of large objects. When a baseball hitter is trying to hit a ball, he or she can estimate exactly where that ball is with some high degree of confidence and its momentum, and guide his or her bat to the ball and reliably hit it. But the funny thing about electrons is that they're so much smaller than everyday objects that it actually becomes significant. Now, why does that have to do with the atom? It means that we can't know, meaning it's truly impossible. Not that we're lacking information or we're lacking in computing power, but we physically cannot know exactly how an electron is going to move around the nucleus. Okay, if we can't know, then why do we bother making models? Well, students, it turns out we can calculate with pretty good precision the likelihood, statistical probability we're talking about here, of where an electron would be. Let's use an analogy. Consider this. You have a firefly. A firefly is, the bugs that come out in summertime and they light up, and then when they stop lighting up, you don't know where they went because it's dark out. Let's say you can't actually see the bug. So picture this. Imagine you're in a dark room. There's a male firefly in it, flying around. In the center of the room is a canister that contains a female pheromone or sex hormone. The male firefly is going to be attracted to it. Since you don't know where the firefly is, what you can do is set up a camera using time-lapse photography. So you're just opening the lens and you're going to capture all of the locations of where the firefly is when it lights up. And you might get a distribution like this. Notice the high density of lights in the center of the room where the attractive pheromone is for that male firefly. Remember, you can't predict where that firefly is precisely at any given moment, but you have a good idea of where it's going to be most of the time. It's going to spend most of its time close to that female pheromone that it's attracted to. Okay, what does that have to do with the atom? Remember, we can't know the exact location and position of an electron. The regions of space where we're likely to find the firefly are kind of like the regions of space where we're likely to find an electron within an atom. Remember, electrons, which are negatively charged, are attracted to the positively charged nucleus. So generally, electrons are going to be near the nucleus. Now, the reason it gets complicated is because electrons, if you have more than one of them, electrons repel each other. And furthermore, because they have a wave-like nature, there's only certain places where they can inhabit. This is a bit like Bohr, and we'll connect to Bohr in a second. Well, in the same way that the firefly generally spends its time near the center of the room where the female pheromone is, the region of space where you can find an electron is generally going to be near the nucleus. We get to draw a border, and we have to arbitrarily say there's some percentage around which we're going to say that's the edge that we want to draw our shape. Where there's a 90% or higher probability of finding an electron, let's draw an edge there. And that is your quantum mechanical model orbital, the shape, a three-dimensional shape where you're likely to find the electron. You could have defined that region of spaces where there's an 80% or higher probability, and what that would do is just draw the edge a little bit further out, but you would retain the same shape. We're going to take a look at those shapes shortly. Okay, one thing to notice, there still are energy levels. Remember in the Bohr model, we had n equals 1, n equals 2, and n equals 3. Well, every energy level has an orbital, and we're specifically going to talk about the spherical ones at first. Those are called s orbitals. S orbitals get bigger with higher energy levels. And so do the other types of orbitals that we'll take a look at. Every type of orbital gets bigger as it goes to a higher energy level. One little note about these particular diagrams, if you take a look, you'll see lots and lots of dots, and you might think, oh, that means there's lots and lots of electrons. No, it's kind of like time-lapse photography with the firefly. We are showing all of the possible positions of a single electron all at once. That's why you see lots of dots. It's not that there's lots of electrons, it's that there's lots of potential positions. Okay. One more way we can relate this to the Bohr model. Electrons, remember, they're wave-like in addition to being particle-like. They're kind of like standing waves. Now, what do we mean by standing wave? Consider this. You've got a jump rope attached to a wall, and on one side of it, you're wiggling that rope up and down and up and down and up and down. As you increase the frequency that you're wiggling that rope up and down, you can get to a point where it looks like the rope isn't moving, even though it is. The individual particles within the rope are moving, but the shape of the rope looks to be the same from moment to moment. They call that a standing wave. And the point at which the wave is not moving up and down is called a nodal point. It's a point where there's no movement of the rope. Well, students, get this. If we have a couple of spherical shaped s orbitals in the n equals 1 energy level, and then another one around it in the n equals 2 energy level, the electrons could be in the spherical 1s orbital, or they could be in the spherical 2s orbital, but there's a gap in between. There's a place between those two orbitals where you cannot find, or at least there's a very, very low likelihood of finding those electrons. We call that a node. Or consider this picture where there's 3 concentric s orbitals, the 1s, the 2s, and the 3s. The spaces in between those orbitals are where you're very unlikely to find them. It's just like a standing wave's nodal points where there's no movement. So there actually is a relationship between the Bohr model and the quantum mechanical model. We're not throwing Bohr out. We're just expanding upon it. So students, if the electron's position is like a standing wave that can accommodate nodal points, consider these two images. that relate to the Bohr model's energy levels. This standing wave, which admittedly is kind of weird because it's going in a circle, exactly fits the average location of that energy level. There's 1, 2, 3, 4 nodal points. Consider this one on the right side. This wave does not quite fit within that energy, within that energy level. That wave cannot, that energy level can't exist within that atom because it doesn't perfectly fit a standing wave. So it's only the standing waves that, as if it were in a straight line stretched between 2 points and vibrating with a certain frequency, that allows nodal points and otherwise non-moving parts of a wave. Looks like the wave itself isn't moving, even though the particles within it are moving. Those are the only energy levels that can exist. Just like in the Bohr model, where there's only certain energy levels where electrons can exist. So consider this one. Here's an allowed orbit. There's exactly 1, 2, 3 nodal points. But consider this one. There's in non-integer value for the number of nodal points. And if there's not an integer value, then the wave collides with itself, and it's called destructive interference, and it can't exist, at least at that energy level, within that particular atom. So where are we left with? We know that electrons have both wave-like and particle-like properties. We know that from the Bohr model, there are certain energy levels in which they exist and thus emit photons from them. Along comes Schrodinger with the wave mechanical model and says, no, look, there's a wave-like nature to this. But Schrodinger didn't just displace Bohr, he reinforced it. He's explaining why electrons in their wave-like nature can only exist in certain energy levels. So remember Bohr's model, n equals 1 is the first energy level. That's when you have one nodal point. N equals 2, you can have 2 full wavelengths, or it turns out there's 3 nodal points in that case. Or in the third energy level, n equals 3, you can have 1 full wave, 2 full waves, 3 full waves, which gives you that many nodal points. So each of the energy levels that exists refers to a standing wave with a different number of nodal points. Okay, all of that is the theoretical underpinnings for what we're going to take a look at and for what is important for us in this class. I do want you to know some, but not all, of the shapes of orbitals because they get a little bit goofy. We're going to ask you to know the S-type orbitals and their shapes, the P-type orbitals and their shapes, and the D-type orbitals and their shapes. You do not need to know anything beyond that. When we take a look at these shapes, remember, they are a three-dimensional solution to Schrödinger's wave function. So we're used to looking at two-dimensional axes in algebra class, where you have an x and a y-axis in a plane. But if you add on to that the z-axis, well, students, now it gets a little bit difficult to visualize this or represent it using a flat screen or a flat sheet of paper. We're going to have to ask you to use your imagination because we're limited by screens and sheets of paper generally. If we could, and there are there are some models, that three-dimensional models that we can take a look at, but we're limited right now. Okay, for the S-type orbitals, their shape is spherical. So just picture a ball with its center at the origin of the x, y, and z axes. That's their shape. Now I'm going to show you another type of orbital. These are a little trickier. They're called the P-type orbitals. Notice they have a nodal point in the middle, and they have 2 lobes or parts sticking out. It's kind of like a dumbbell. You know, if you were to grip a dumbbell in the weight room, the part that you grab with your hand is the nodal point, and then there's 2 heavier, larger parts off either side, and they're symmetrical. so you have an equal probability of finding an electron on one end of the lobe, or one lobe as the other. Their dumbbell shapes are oriented along one of the three axes. And so we name them for the axis along which they're oriented. So for instance, the P with a Y subscript orbital shows the probability of finding an electron with high likelihood somewhere along the Y axis. Aha, if we were to draw this in a smooth shape, it would look like this. The P subscript X orbital is a dumbbell shape where there's a high likelihood of finding an electron somewhere along the X axis. And the P subscript Z orbital is a dumbbell shape where there's a high likelihood of finding an electron somewhere along the Z axis. Okay, notice there's three different kinds of P orbitals. That'll be important as we move further along in the lesson. So three kinds of P orbitals, one kind of S orbital, just a sphere. Now we're going to take a look at the D orbitals. These are a little more goofy. There's 5 D orbitals. The general shape can be described as kind of like a clover leaf. It's like a double dumbbell. You got 4 lobes. They're oriented in a particular plane. So any 2 axes make up a plane, and it's in that plane that the cloverleaf shape is oriented. So let's look at the top 3. The D subscript YZ orbital is in the YZ plane. So the axis that points in and out of the screen and the axis that points up and down within the screen forms a plane. And in that plane, you can have a cloverleaf shape with 4 lobes. That's the DYZ orbital. The DXZ is consisting of the x-axis and the z-axis, forming a plane with a cloverleaf shape in that plane. Or perhaps this one's the easiest to see. The D subscript XY orbital exists in the XY plane. Notice the axes here. So this would be the flat plane that comes in and out of the screen. And the cloverleaf points in between the axes. So like the X and Y axes are oriented at a certain, they're 90 degrees from each other. Well, they would be 45 degrees from where the lobe is pointing. Then we have down at the bottom 2 other goofy ones, dx squared minus y squared. Here's a cloverleaf shape in the XY plane, so that the plane in which they're found is indicated in the name. But this time, instead of having the vertex of the lobe pointing in between the axes, now the vertex of the lobe is pointing along the axes in the same place as the axis. And then perhaps the goofiest one of all, the dz squared is along the z-axis. And instead of having a dumbbell shape or a cloverleaf shape, it's shaped like a dumbbell. It looks kind of like a p orbital, except it has a bonus thing in the middle. It looks kind of like a donut with a dumbbell. So that's why I say at the top here, one dumbbell with donut shape. I know those are goofy shapes, but when you see them in pictures, I'd like you to be able to recognize